Hello, I'm Mark Dye.
And I'm Mike Dye.
We're juniors at Harvard State School located in Studio City, Los Angeles, and this is our project, NeuroGaze.
ADHD affects millions, and traditional screening is costly and subjective. Our study explores eye tracking as a reliable, accessible alternative. Using NeuroGaze, we analyze reaction time, fixation stability, and impulse control to distinguish ADHD from neurotypical participants. ADHD diagnoses have increased significantly, yet current screening methods remain costly and subjective. 10.47% of U.S. children and 6% of adults have been diagnosed with ADHD.
These diagnoses often rely on subjective tests, which can lead to biases, misdiagnoses, and high costs.
Our hypothesis: if NeuroGaze can track and analyze eye movements, it may provide a reliable, objective ADHD screening tool by identifying distinct patterns in reaction time variability, fixation stability, and impulse control.
To conduct our study, we developed a custom-built eye tracking platform. We use laptops with webcams for consistent eye tracking data collection. The backend of our platform was built using Flask and RESTful API, with data analysis performed using Excel, Python, and Jupyter Notebook.
Our study followed a structured four-step procedure. First, the initial calibration. Second, the visual attention test. Third, the continuous inhibition test. Lastly, the interference test. A visual representation and detailed descriptions are provided on this slide.
To analyze our data, we used a histogram for reaction time distribution, a box plot visualizing commission and omission errors, a correlation matrix to draw comparisons between key variables, and a heat map to visualize eye tracking movement patterns. On the slide, you can see our different graphs represented: histogram, bar graph, correlation matrix, as well as heat map. Our key findings showed that ADHD participants had a higher reaction time variability, confirming its link to impulsivity. Greater variability also correlated with lower test performances. Lastly, ADHD teens exhibited significantly lower fixation stability, indicating attention difficulties.
While our findings highlight the potential of eye tracking for ADHD screening, a few limitations of our study should be considered. Our primary difficulty was our small sample size, as we only had 13 ADHD participants and 47 neurotypical individuals. In the future, a large sample would be required for broader conclusions. There likely may also have been environmental variability, as different focus levels and distractions could have caused differences in gaze accuracy.
Our study highlights eye tracking's potential for ADHD screening. Future steps include increasing ADHD sample size, validating findings for clinical use, and improving WebGaze's algorithm. More broadly, objective eye tracking could aid in detection of other neurodiverse conditions. Our study demonstrates that eye tracking holds promise for ADHD screening, identifying differences in reaction time variability, fixation stability, and impulse control.
We found that higher reaction time variability correlated with impulsivity, as ADHD participants made more information errors. ADHD teens showed the greatest fixation instability, reinforcing attention and control challenges. Overall, commission errors were higher in ADHD participants, reflecting impulsivity.
However, reaction time alone wasn't a reliable marker, and omission errors didn't strongly correlate with reaction time variability.
Even so, our results suggest that eye tracking can be an objective, scalable tool for ADHD screening. And here are the sources.
And these are the sources we used for our slide. Thank you.